Today, I'm going to present a stochastic SRS model in discrete time to describe the weekly reported influenza data in the province of Manitoba. Just to let you know that this is a basic about preliminary results of joint work with the Shaman Dean and the Mahmoud Torabi. This presentation will cover the following. Sorry, I want to put in the full screen. Okay. So this presentation, I will cover the following points. So I start with describing data that will be analyzing. So, and I will just mention some preliminary results about the model we are proposing. So through simulations, and I will present some data analysis or related results as well, and I will finish by giving some conclusions and presenting some ongoing work. Now, just a little bit about the data that we have. So this data, as I said, data from the public health of the province of Manitoba. So they are surveillance data. And in general, in Canada, there is a system of about surveillance of influenza and likely flu illness where they publish weekly reports about the influenza activity. But our data are particularly came from the public health of Manitoba, province of Manitoba. So if we just try to observe how data look like, so I try to to present data by year or by season. So as you see, this figure shows how the epidemic activity gradually decrease after week 10. Then from that, the low values are observed from week 17, from week 17 up to week 47, 48 almost. So, and as you see also, there is almost no activity of influenza during the summer period. So we can also try to observe this data in the other way. So as if we saw it or if we observe it like a time series, so it clearly shows that the data exhibit pronounced seasonality, where the intensity of the flu varies from year to year. So you should observe it. And usually we can say that the high activity of influenza is observed between I can say between weeks 52 and the week 10, more or less. So here, just we observe the seasonality within our data. So, but we are not quite sure if there is some more trend in terms of time series, or even the question should be, how can we just quantify the correlation level between present observation and the past ones, or between present observation and the past value within this time series. So talking about seasonality, talking about the time series or other characteristics, and considering that our approach will be just using a compartment model. So I want to go through some basic model of compartment models. So the classical deterministic in continuous time is the SRS model, or susceptible, infectious, recovered, or removed depending on the kind of the disease. So this model just shows how the transition between different compartments of the model are done. So basically, the first question is about the change, the relative change of the susceptible over time. So this second question just shows the rate of change within infectives. Then here we will just see how the number of recovered from time t according to what you had within the infectives compartment. So some assumption here are the population size is considered to be constant, and the transmission rate and the recovery rate as well are constant. So we cannot see this transition through the flow diagram. So where, as I said, there is some force of infection that is exerted to the susceptible, and this is due to contacts between infectives and susceptible. So, and as you know, there's a probability that this contact results in infections. Then from the infectives compartment to the recovered compartment as well, we have some more proportion of infectives that are recovering from the disease. So as our model is a SRS model, means the susceptible, infectious, recovered, susceptible as well. So we should see the model in this way. From the previous slide, I just showed the same graph, the same plot here. So, but here I'm just trying to add the other arm, which shows some probably, like here we are assuming some partial immunity from those who are recovering from the disease or from infection. So where there's also a proportion of those people, of those individuals who already recovered. So also becoming susceptible once again. So this approach, or this kind of model is seen in the continuous time, as I said, but our objective is just to, or depending on what we are observing, we try to model the dynamic of the disease considering the discrete time. So there is some more justifications about reason why there is switch from continuous and deterministic to discrete time and also stochastic. So first of all, there is a nature of the data that we have, and also is due to, and this is due to some confidentiality about the same data. So sometimes it is quite difficult to have access to for individual level with data. So that's why sometimes it's just people trying to come up with a model that allows to use the aggregated information. So this approach just allows the combination between some statistical model and the nature of the data, as I said. So the first extension from this deterministic to stochastic was from the Bayes in terms of channel binomial model, which this model is basically a discrete time stochastic, where they assumed that the probability of escaping infection disease during a small time, delta t, so will be governed by the number of in this case will be it due to the time if we can say it will be just basically due to the time to event. So as if we know, for example, if we assume that the infectious individuals exert a force of infection on the susceptible, so the force of infection, just you can think beta times IT. So, and this force of infection is being exerted in the within time period delta t. So the number of events that should happen in that time, so there should be considered in two ways. So either we just should talk about the new infected, or we should talk about the new recovered during the constant time. So when we talk about the new infected, so we assume that the probability of no event or no any susceptible individual that will catch the disease, it will be given by this expression. So thinking about the Poisson process. Then, so in the other way around, the probability of getting at least one person or one susceptible to get infected will be 1 minus the probability of not being infected. So assuming they have a fine number of susceptible, so they came up with this with this binomial distribution, or to model the new infected or the new recovered, considering to the rate of change within the number of those who are recovering from the disease. Now, this was just in terms of extension from the discrete time to from continuous time to discrete time, and also considering some discrete deterministic model to stochastic model, just introducing some statistical distribution. But coming back to our data, or to the time series as I presented, so there is also the other approach from which combine the compartment model with a time series. And this model was just developed there's a lot of work according to this approach. So many papers were published in this framework. So where this model were developed to forge a link between the theoretical epidemic modeling and the statistical approach to the time series. So that's why it comes the name from time series SRS model. So the other input as well is just to consider the transmission rate to vary over time, as we saw in the previous slides. So there is an assumption about the transmission rate which is constant, but here is being considered as a function of time either in a deterministic way or as a periodic function. So from these ideas and considering the nature of our data, we are proposing the model in this framework, but where first of all we need to know, or just from the data that we have, we really want to understand the degree of correlation between the present values within our time series and the past values. So means that we want to see the which autoregressive order that should be considered to model or to describe the dynamic of this time series. So also we are wondering if is there any term of moving average, or either if there is some trend. So to try to understand those, we try to use what I should call the empirical way. So where this was used to function the ARIMA in combination with the Fourier terms of the process. So ARIMA is a autoregressive integrated moving average, where it is a model that combines, as I say, autoregressive. Want to see if there's some degree of differentiating, and also want to see if there's some moving average terms. So also the Fourier terms allow us to just to see which order, or how many set of pairs from the periodic functions should we use in our model. So this exploration was made through our package, the R package for forecast. So then we tried to select the model. So using based on the IC criterion, and after fitting the model to our data, so the optimal or the reasonable model deserves to be the ARIMA for 200, means that there is a autoregressive order 2. There's no differences, and it means that our series is just stationary, and there's no moving average term. So as you should see here, in this graph, which I call the best fit. So which is the best fit of the time series from 2012 to 2015. So it showed the rate at the estimated and the observed at just the true time series. So I could say that this fit is near to the it just is fitting well the data. So from this information, or from this after this exploration, so we try to transform the information got from this preliminary analysis of the information got from this exploratory analysis to within a compartment model. So which is this one. So in this model as well is in the framework of time series SR model, but with the other S. So means that we are allowing some partial immunity within when the people are recovering from the disease. So the IT is the reported or reported weekly number of influenza at time T or at week T. so which is distributed as Poisson with the mean lambda. Then the mean lambda is just a function of the previous number of susceptible in the previous one period before. Then here also we try to incorporate the information got from the preliminary analysis using the empirical model. So here we we assume that the new infected depending on the infected that we had at least within within last 2 periods. So here there's other new term, so which is PT1. So this term is, we are assuming that maybe should not about the infectives within previous period with where the new cases just are depending on. Probably we should assume coming or influx of new people who come, maybe who should be infected as well. So, and also here we are assuming that the transmission rate, as I said, to be a function of time, where this VT will be, oh sorry, I think it's not quite seen. Will be a function, a free term where the number of pairs that we are considering are 2. So basically the stochasticity in our model is based on the new infectives within our area. Then also we are assuming some people who are coming in should be just, we are trying to model them using a Poisson distribution as well. So also we need to update, as we are talking about a time series. So we need also the update within our susceptibles. So the update will be due to what we had in the previous time. So we remove those who were infected. Then we try to assume that our susceptible are maybe there's some already recovered who are losing the immunity. Then they become susceptible once again. So in the same way, so we assume that there's some update within our recovered individuals through those who are recovering from the infection, but also we have to think about those who are losing the immunity. So basically, this is the preliminary model. Just we are trying to explore in terms of time series. So, and just to understand or to do some more calibrations of the model, and to have some more information about the different parameters of the model. So we ran different simulations just to see what within different scenarios. So how model will behave in terms of modeling the dynamic of the disease. So here I will present some more result just to give you some idea about what the simulations are giving us. So here, as you see, considering the model, just the presented model, but here I'm not considering the influx process. So when I'm talking about the influx process, they are just I'm talking about the P process, about those who are coming from, we assume to come from outside. So here, as you see, just we should try to understand the second row about the infectives. So the model shows the outbreak of the infection, but as you see, over time, the infection is fading out or is dying out. So, but there is no way, or it doesn't show a new outbreaks. So, as you say, comparing to the data that we have, so there is no seasonality in this way. When there's no like when we don't consider some some influx people, or maybe people who should come outside. So our model is just, it doesn't capture the seasonality as we were expected. So then maybe so to confirm if there is this the parameter that just capture this phenomenon or this process, if it just should be interesting or should be have some impact in our model. So we tried next to incorporate the model, the parameter in our model. So here we are just to try to incorporate it, just to take the model, the same model, but incorporating the process that indicating the influx of the people, the indicating when people are just are coming. So as you see here, there is somehow the difference between the figure 6 and this figure, the previous slide, where in this case there is the model is trying to capture the seasonality within the seasonality over time. And also if we see the number, there's also behavior of within the susceptible, where just there is some, when we have outbreaks, or when you have there's epidemic, so the number of susceptible decrease, and after people are getting recovered, also the number within the compartment of recovered, so the number of recovered individuals so is increasing. So, but here also when you see in the case, some people are losing the immunity, so we see that there is some increase in the within the number of susceptible. But here also, as you see, it's not proportional. The way people are losing maybe they're losing the immunity, and people, if they are just joining the compartment of susceptible. So I think this is due to some randomness in our model. So after that, we tried to we tried the different simulations and the different scenarios within the model, but I didn't just put all them here in the presentation. So after that, we try to feed the model to the data to see how the data, or how the model was fitting the data. So before going to or moving to the data analysis, I would like to mention that we are using the Bayesian statistical approach. Precisely, we are using the JAG and R just to fit the model. So beside of just trying to different scenario within just trying some different form of the model, also we had to do some more sensitivity analysis within the prior distributions for our for our parameters, just to try to see which distribution, which prior should be best for our model. So here, these are the results from data analysis. So these are the posterior distribution for our parameters. So for each distribution, for each posterior distribution, we show the mode and the highest density interval. So just to give you some idea about the fit of the model. So these are the first parameter, and in the next slide, so it comes the other posterior distribution for the other parameters in the model. So what I should comment here for the posterior distribution of parameters, for those parameters, for what you should see as a regression parameter was we consider the normal distribution as prior distributions, and the other parameters which has a support between 0 and 1, we took them, the prior distribution was beta distribution, and the parameter like lambda, which is supposed to be, should be positive. So we assume a exponential distribution. So basically, then also in terms of convergence, the diagnostics, so the convergence was pretty good. Then we show according to the SAMU convergence criteria. Then we used the coda package also from R, just to monitor the convergence of the distributions of the posterior distribution of a parameter. Then after getting the posterior distributions for our parameters, so the next step was just to try to see if our model should be reasonably, our model is not fitting the data as we should like. So here also we try to compare the results from the model that we were proposing to the other model, just as we did during the simulation process. So the first step we did just was to feed the model to the data, just to estimate the parameter under the model without, just where in the free terms, instead of considering two terms as as we were assuming. So here we feed the model just considering only one pair in free term, to see if there is any, so to see what will happen to considering to the seasonality within our data. So as you see, there is the model is not capturing the seasonality comparing to the data. The red curve, the red curves are the fitted model or are the simulated model from the posterior predictive model. Just here we use the visual checks using the posterior predictive, where we simulate 1,000 replicate from the fitted model, and we wanted to compare to observed data to see if the fit, or if the simulated or the fitted model has the same, just capture the dynamic of our disease. So, but as you see, there is some more discrepancy within the compared to fitted model and the true observed data. So this model was not fitting well. So then after we tried to, in this time, we fitted the model with the true model to the data. Then we did the same, just using the posterior predictive check, where we simulate the same 1,000 replication from the fitted model, and we just plot together with the observed data. So at least comparing to the previous plot, so this model is trying to capture the seasonality for the data, but still they may somehow, it's not just trying to get or to capture this point here. So which should be like somehow there's somehow the underestimation, or in some cases overfitting. So maybe here this model is relatively fitting well compared to the previous, as I said. But I think we think that there's some we should improve just to within some in terms of some assumptions we made, or we should just incorporate some components in our model. So just for summarizing this small talk. So as sometimes when you want to explore the data, maybe the empirical way should just help to understand the behavior of within the data. So for example, here we use the empirical way or phenomenological model. So without just taking into account the basic physical laws or mechanism of the infection. Then after we came up with some more characteristics or some more insight that are helping us to just to improve the proposing TSIRS model in discrete time. So here also we showed the way the proposed TSIRS model was fitted to the data. So, but even though we still trying to accommodate some assumptions or some just to improve the model. So also for the Bayesian approach that we are using allows us to get some prior distributions for parameters, and also as well to try to find the posterior predictive distribution, which also we use to compare the fitted data to the observed ones. So as I said, the model I can say is not the best one. So we still, there's some more limitation. Maybe we have to consider in doing within an ongoing work. So among them, so we are not just incorporating, for example, some more demographical factors. We are not taking into account some some more factors due to vaccination. As you know, every year there is some more vaccination campaign. So also, if we are considering some more newcomer as infectives, so maybe also we should think about some newcomer as susceptible, because also they should increase the density of the And as we saw, the transmission or the infection process is due to the contact between susceptible and the infectious. Also, we should the model doesn't account the covariate. So maybe also these are also there's some more thought about incorporating environmental and social economics covariate just to improve the model. So for the in the ongoing work or what we are doing right now, just try to not only to consider the time component, also to see how we should combine time component and the space component just in the spatial temporal model. Also, as I said, this data was for the whole province of Manitoba. So, but maybe you should try to go down, just to consider different regions in the same province, just to see how to compare or to understand the maybe spatial distribution or spatial dynamic of the disease through different regions. There's also other ideas about joint modeling, the multiple outcomes. So here should be modeling jointly the different outcomes from a given disease, or modeling jointly the different disease. So if I just as we saw in the previous talk, so there we saw different diseases which are modeling in this. Maybe it's not the same approach, but I think also this should be considered. So I end the talk by acknowledge the NSRS and the CNSSI CRT for the financial support. So thank you very much. Merci beaucoup.